So remember, we also have the third thinking question of the two different massive balls rolling down the slope and which one reaches the ground first. Now, to answer that one, we need to introduce one more concept, which is the normal force. The reason why that is the case is because now we've introduced a new ingredient. We have actually we have them rolling down the slope. So the slope will actually, if you remember how to draw free body diagrams, right, it will produce a normal force, and that plays a small role into this analysis as well. So we'll need to understand how that works. Before in the other two examples, whether they're both free falls, even with air resistance, you don't sort of have an extra surface. Now we do. So the basics of normal force, it's sometimes one of a more confusing one because it is one of the more trickier ones. It is actually very subtle if you go in depth how it actually works on the microscopic and the atomic level. So we won't really go there, but the reason why it is slightly tricky is it's one of the only force that actually changes its value or adjusts depending on what forces is exerted on it. Okay, so I'll show you what I mean. All right, so first, if I want to analyze the free body diagram of this box, right, put it on the table. So let's start with the easy one. We'll start with the gravity, right? Gravity will produce a weight like this. All right, so you can use G, you can use W, either way. Since we just learned W, I'll get you used to both as well. Now, what other contact force is there? Well, there's a table. So there will be a normal force. We know that, but except for that, anything else? No. All right. So that's the only other one. So let's say we don't know what is a normal force, right? And if we don't know what is a normal force, this is sort of the only force there is. But that can't be, because then this would be falling. This would be accelerating downwards. This would be in free fall. So if you put the box on the table and if it's not going anywhere, then it must have something counteracting this force. So this is why we give it a name, normal force. Okay, so this is how it looks. And as you notice, I've drawn it as equal magnitude with the weights, because that is the only way it can make sure this stays stationary and doesn't accelerate, right? If you have a net force, so now my net force is actually 0, right? If I have a net force, this will start accelerating either upwards or downwards, which is not the case when you put something on a table. Okay, so it's called a normal force, like I mentioned a couple of times already. It's due to the word, mathematicians use the word normal when something is perpendicular, which means when something forms a 90 degrees to something else. So if my slope is at an angle, then the normal force will be also normal to the surface of contact. So this is the surface of contact, and the normal force would be this way, and gravity or the weights would be this way. Okay, so we'll get back to that in a second. And I want to address one property over here, right? Is the normal force reacts to and adjusts depending on how much force you actually impart on it, on the surface. Okay, right? So as usual, the normal force is a force on the object from the surface, but the value of it depends on how much force is imparted on that surface. Okay, it depends on this. Okay, so what do I mean? Let's say I have an object with a mass of 1 kilogram. Okay, so what is the weight? Well, the weight is, well, mg, right? So this is just 1 times 9.81. Okay, so that's 9.81 newtons, or 9.8 if you want to round it to just one decimal place or two significant figures. Because it's not going anywhere, right? I'm not going to draw the table. I'm just going to draw the object of interest. Then if it's not going anywhere, then I need n equals to w, right? That's the only way to balance it out. The magnitude, notice no vector signs, right? No vector signs means the magnitude of n is the same as the magnitude of w. And in this case, right, so n will also be 9.81 newtons. Okay, now let's, if I change the scenario, if I start adding a pushing force on top of it, right? So if I now push the box downwards, so what are my forces? Well, I have a pushing force downwards. I have the box's own weight and also contacting the table. So the table will produce a normal force. Okay, so this is my free body diagram if I add a pushing force. Okay, so if I push on it. Okay, so what will be the balancing equation over here? Well, the balancing equation would be, well, n must equals to w plus p, right? So let's say I push it with 5 newtons of force, right? And same thing, right? 1 kilogram of the box, right? So the weights would be mg plus 5, right? And like I said in my tip, yeah, let's not plug that in. So here I'm just using the formula. Let's do one thing per step, right? So this step I'm just plugging in the formula, and now let's plug in the numbers, right? So this is 1, this is 9.8. I'll keep it simple, and 5. And as I shown you another tip before, when you're doing intermediate steps, you can suppress all your units if everything is the same unit, right? So this is everything is a force, so everything's going to be newtons. Don't worry about the unit at the end. Just put back in because otherwise you'll be carrying a lot of units. It's up to you, but I generally don't do it. And that would give me 14.8 newtons. Can you notice what happened to my normal force compared to example A? It increased. So this is one of, that's what I mean, is this is one of the, I want to address, this elephant in the room that is one of the weirder force that it actually reacts to how much force you apply to it. And give you one more example. This time, let me pull it. So I have a string and I'm going to pull it up with force. In this case, it's going to be called a tension, right? Because with a string. And with, let's say, 0.1 newtons. Okay, so just pull it lightly. All right. So the 1 kilogram box, same thing. So what's my free body diagram in this case? Well, then I have still the contact force from the surface, and I still has its weight like this. Okay, so what's the normal force in this case? Let's calculate n. But first of all, what's my balancing equation over here? If everything is static, if the box is not going anywhere, right? If it's not accelerating upwards or downwards, then these two must add up to, the magnitude of these two must add up to this. I probably should draw a longer arrow for W, but just want to save some space to write the equations over here, right? So these two should add up to this one, right? So what is N? N is W minus T, right? Immediately you'll see the N, the normal force, is a little bit less than W already, right? So let's directly plug the numbers in. Let's not do this again, but if this is the first time I'm doing it as a part C, but if this is the first time you're solving a problem, this would be the more complete steps you want to show. So now I'll just plug the number in because I've chosen easy numbers, minus 0.1. So the normal force, as you can see, is a little bit, right, tiny bit. Remember the units at the very end. It's just a tiny bit less than if nothing is pushing or pulling on it. Okay. Now, be careful for one thing. So here I've sort of justified this point, but now I want to clarify one thing. Don't go overboard, right? So what do I mean? This is the last example over here. If I start pulling this with a tension of, let's say, 2.5 newtons, okay? Now, what's the weight? Well, the weight is still going to be the same, right? Let's make, yeah, I need to make that larger than weight. So let's say 12 newtons, like that. Okay. So the weight again is 9.81 newtons. All right, let me suppress all the units just for clarity. Okay, so should I still draw the normal force? Now this is the case where if you pull it larger than its own weight, right? Then there will be no more normal force because even if it's touching in this instant, the next immediate instant, it's going to be off the table. It's going to accelerate off the table, right? So the normal force, the minimum value of normal force is 0. Okay, so if you're not sure, what you could do is you can draw this as well, and then do the same analysis as we did there. Let's see what happens, right? So sometimes in physics, you want to also learn how to explore on your own with the same concepts. So now that you know the concepts, let's see what happens when you take the concept and the same concept and explore and see what happens with the equation and not just memorize some of the things, right? So the normal force would be W minus T, and then W is 9.8, and that's 12. Okay, so what do we get? So we get 2.2, and sorry, negative 2.2, all right? That's almost around 10. If 10 minus 12, that's 2, or negative 2, but that's a little bit more, so 2.2. Does that make sense? Well, the magnitude of this cannot be negative. So what I'm showing you is, let's say, because I could just tell you the fact that, remember, if this is larger than this, don't include the n. But that doesn't give you a good understanding, right? You want to be able to figure this out on your own. The whole idea is to learn the concept and take this and see if you can actually analyze the situation. So this is how you would do it, right? So let's say I haven't taught you what happened when this is larger than this first. So you take your concepts. Let's see if you can take all the things you know about forces and everything and see if you can deduce your own answer. So I'll guide you through it during the lectures over and over again throughout this course, and slowly, hopefully, by observing how this is done, how physicists look at these situations, you will start to be able to develop this logical deduction skill, right? So the start over here is, all right, so the first thing I learned is there is a contact over here, at least before it lifts off the ground, that will lift off the table. It's still, there's a moment that it's touching, all right? So let me draw the n first and see what happens. I know I'm pulling it with that much, and then the weight is that much by previous calculations. Okay, so I've learned how to do that, so I'll do the same thing, right? So this plus this should equals to this if it's in some sort of equilibrium. And then I want to find out what n is. So let's isolate it, right? Make that the subject on the left-hand side and move everything to the right-hand side, and I get a negative number. So first of all, I would be a little bit concerned when I see this, right? If I were you, I would be like, this is a magnitude. Magnitude cannot be negative. All right. So what else can negative means? Well, negative could mean going the other way. Even though I'm like here, everything is set up in a magnitude way. But maybe, maybe this is just the other way. But it couldn't be. Why couldn't n point the other way? From what you know about normal force, in fact, I think it's on either this board or before. Because normal force is normal from the surface, right? It's whatever, it's a contact force, and it's always gonna, if it's contact in this surface, it exerts a pushing force that way. So it is impossible to have the normal force pointing downwards. So what does that mean, right? That justifies what I told you in the first state is the minimum of n can be 0, right? The lightest, if I pull it with exactly 9.8 newtons, then I will, if I pull it with exactly 9.8 newtons, I will get 0 normal force, because my pulling is just balancing it. The table is not doing any more work with holding up the box, okay? And if I pull it more than that, well, I have two comments. First of all, the normal force should not exist anymore because it's lifted off the table, right? So that's the reason why you should not even include the normal force in your analysis. And comment number two is it possible that it's in equilibrium? Like here, I've assumed that the state is in equilibrium. When I say it's in equilibrium, I mean it's not accelerating, it's at rest or constant velocity. That's what equilibrium means, either at rest or constant velocity. But let's just keep it simple, at rest. But it's impossible, it will be at rest when this is larger than this. There is nothing else. In order for it to be at equilibrium, you must have all the forces sort of just balance everything out to have a net force of 0, right? From Newton's first law. There's nothing else counteracting the extra bits other than the weight. So if you pull it larger than that, not only the fact that you won't have n, you won't even have an equilibrium, which means the whole analysis is wrong, okay? And what you should be doing is you should be, you write it separate so you can compare that, right? So you shouldn't even use this. What you should be is using the non-equilibrium formula where you have an acceleration. You use Newton's second law, not the first law idea where there's no net force, right? This is a special case of no net force, right? So you should be using this where t minus w, and in that sense, you can actually calculate, etc., something like that, right? You can actually calculate the acceleration of it. Don't worry too much about this just yet. We'll talk about that we'll show you more examples in tomorrow's lecture. But yeah, so these are the key properties of the normal force. And just to recap, the first property is it depends on the applied forces imparted on it, on the object. And the second is n is always larger or equals to 0. It cannot go less than 0. So you have to use a little bit of common sense to analyze the situation with this point. Okay.